Okay, good morning. And as Professor Chakraborty said, that I will be discussing mainly the characteristics or properties of the MOS transistors, and then also we will look into the inverters, MOS inverters. Now, you have already been introduced about the basic logic circuits using CMOS devices. So, our objective will be now going down further below, in that we will examine the what is how the current voltage equation, so that of a MOS transistor, how it is derived from the basic fundamentals of the of the device characteristics, and then we'll slowly build up the case for the MOS inverter. Now, to begin with, I guess this is a somewhat heterogeneous mixture, where some students have gone through the semiconductor devices course and some haven't. So, those who have gone through, maybe you will find that some of the things I am talking are probably too preliminary. Those who haven't may find that I am going through little bit faster, but I have no choice. I will try to confine the basics of the MOS devices as such. Now, to begin with, you have already seen what is a MOS device or MOSFET. Or now, MOSFETs can be of two types. Normally, we use what is called an NMOS, and the other is called the PMOS. Where N stands for the N channel MOS, where the channel is basically dominated by electrons, but in case of the in the carriers, in case of a PMOS, will be holes. Now, the for fabrication it has three terminals. One is the source, another is a gate, and the third is a drain, and also we have the substrate. In a typical PMOS NMOS device, if you see it, it is fabricated using a p-type substrate. That means on a silicon you diffuse or make it by group 3 elements, and so that it becomes p-type devices. I think you have learned about what is a p-type and n-type materials are. So, this is a p-type substrate, where it is a lightly doped p-type semiconductor. Now, to create the source and the drain, what is normally done, you create on top of, now in case of a n-type MOS, we will need that the source and the drain both will be of n-type material. So, therefore, what will happen, that we will create, there are many approaches for inducing the some of the portion of the device as a n-type material. One simplest way is that you create some sort of called well. So, this is a well. There are technologies which will use two wells or a single well. In this case, we are using two wells. So, therefore, in this region, we essentially isolate the part of the substrate using a silicon dioxide, and then in this region, in this well, we first heavily dope it with n-type material, so that it becomes now an n-type semiconductor. So, this becomes an n-type semiconductor. PD also is an n-type semiconductor. So, we have here more electrons here, and similarly this is also in the source there is a more electron. That is the basic source and drain. And the third region, third control, that is a gate, is fabricated by creating some sort of a capacitance. So, that what you do, you deposit silicon dioxide or some sort of a dielectric, mostly silicon dioxide, on top of this p-type substrate, and on that so therefore, there is a very thin layer of silicon dioxide is deposited by, there are many methods, and it can be done by chemical vapor deposition, it can be done by other techniques also. With those, when we will go through the fabrication aspect, it will be told you, and on top of it we put the electrode, that means metal deposition. This is a black part is a metal. So, metal can mostly used are aluminum, and then we have the gate contact, that is the you take out the wires. So, we can have in sometimes we will use a polysilicon also for connectivity. So, you will later on see that polysilicon has a good conductivity as compared to the pure silicon. So, but it is easier to fabricate. So, we will have a source, this is source terminal which is a metal, drain terminal, again we can think it of as another metal terminal, and the gate. So, therefore, we have, and lastly this substrate is also connected usually to the source, but you can give a bias later on in some circuit we will see that we can bias the substrate at the fourth terminal. So, now what happens, you have seen that this is a typical NMOS transistor. In case of a PMOS, the things are reversed in the sense that we have an n-type substrate, and on top of it the source and the drain will be p-type material. Otherwise, the geometry and looks like it will be the same, excepting that the sizes of the transistor will vary depending on, we will see that why. But so, to begin with, so now we have, suppose we have this type of device available to me. This is my transistor. Now, how this thing, you have seen the characteristics, probably it already discussed in the class, that what is the characteristics of this kind of device. And the channel, by the term channel, or is used, is the region between the source and the drain on which the gate is there. So, this is called the channel region. Why channel? We will see slowly. Now, in this channel region, as you can see, it is essentially a p-type substrate. So, whenever you have an n-type material, you have an n-type material here and you have a p-type substrate. If you do not give any bias on this, there will not be any current flow because there is no electrons available. So, there is a more electron in this region and more electron in this region, and now how there is no current path directly. And we will slowly see how actually the current channel is established. So, if you have any doubt or any question up to this, details of the fabrication you can see later on. They are present technology wise. What we would like to do is just reduce the sizes of this region, each of these regions, source region, drain region, and the channel. Normally, you will see that we talk about microns, say some micron technologies today. Essentially, it says that what is the length of the channel itself. So, that if the channel length is less than micron, then we are in the submicron technology slowly. Today, you will find that we have 0.18 micron or 0.45, it slowly went down. Initially, it was about 5 micron, then 2 micron, and technology slowly we are shrinking. The idea here is that to shrink this channel as much as possible. There are certain consequences of it, we will see that later. But all the compaction in VLSI are essentially related to this reducing the size of each of the drain and the source region, as well as the channel length and the channel width. It is a two-dimensional, so the channel width will be there. Now, coming back to the basic understanding of how the thing works. See, if you look at the initially, so this is an N plus region, this is the source, and this is the drain, and we have the gate here. So, what we do normally when we try to use this transistor to look at its current voltage characteristics, we can bias the gate and the source. We can give a voltage, you can apply a battery or some sort of a voltage supply between the gate and source. Say for instance, if I put plus, that is gate is made positive with respect to the source, or we can make gate negative with respect to the source. And similarly, we can apply a potential difference between the drain and the source. Since it is an N type, we will like that the VD will be positive with respect to the source. So, now all of you are little bit familiar with the p-n junction. So, what has happened, if you look at it carefully, this is an n-type material and we have a p-type substrate. So, this is typically an NPN, the p-n junction diode. This is called the depletion region. Similarly, here there will be a depletion region in this region between the n-type source or the drain and the substrate. But unlike in transistor, where the current will, if you look at the base region where from n-type pure bipolar transistor, where we have the n-type both side and the p-type base, the flow here will be controlled by the usage of the gate. So what happens here now? Suppose that initially the gate and source voltage was 0, so they are all open. So let's say this is open. As I said that this is an n-type material, this is an n-type material, and you have the p-type material here, which is hole. So no current can flow from here to here, even if you apply a voltage VDS from here, because electrons from this region, when if you want to propagate or to flow to the drain region from the source to the drain, it finds that there is no carrier available in this region. So there will not be any current flow usually. Of course, if you apply very high voltage, that is different. But usually there will not be any current flow. Now let us try to see what happens. If I apply a gate to source voltage, that means suppose I apply the gate, make the gate positive with respect to the source. What happens now? This side of the plate, this is a capacitor, pure capacitor type of material you are doing. So the two plates are here between the gate plate and the substrate. Now if you apply positive potential here, this positive voltage, what it will do, it will repel the holes from the region below the gate. Now these holes, as it goes, is repelled from the surface, slowly the acceptor ions will be exposed, but still there is no current carrier available, no mobile electrons available now. However, if we go on increasing the voltage, a time will come that this place will be completely devoid of any mobile carrier. So that means this is why initially you have an induced this is a depletion region. So the depletion region slowly gets become wider and wider, and after some time when the DGS is sufficiently large, now you will have the electrons which are minority carrier in the p-type substrate will be pulled towards the gate surface, and then you will have electrons available. So now the material characteristics now effectively changes from p-type to n-type sometimes. So on the surface layer now we have a more mobile electron carrier, and this electron carriers now establishes what we call the channel. So the channel is established as we go on increase the voltage between the gate and the source. In this case, gate should be positive with respect to the source, driving out the initial majority carriers p-type, that is holes, from the surface down to the substrate, and slowly opening the acceptor ions. And then as I go on increasing the voltage, at a point will come when, as we will see from the basics of I'll come back to that diagram later, then you will have this material now becomes slowly you have an n-type channel will be established. Now moment n-type channel is established, and if I apply a voltage between drain and the source, now the drain being positive, electrons will be pulled from the source to the drain, and that will be drift. So here the current is primarily by drift of the electrons. Drift dominates it. It's not by diffusion like in your PN junction, pure PN junction. So here you have so the electrons will flow from the source to the drain as we go on increasing the VDS. So that's the basic philosophy. So therefore you apply the gate voltage to sufficiently large to create a channel. This is what we call the inversion region. Inversion means the property of the semiconductor, which was hitherto a p-type material, becomes effectively an n-type material, and then establishes a channel. So in this region now, so this is called induced channel. So the induced channel electrons now will start proper flow from the source to the drain as you apply the voltage. and now the current flows. So, effectively now you can see the gate that the term correctly suggests is essentially acting as a control input, and the control input behavior is that whenever the gate voltage is sufficiently low or negative or below a certain threshold, the term threshold is used, there is no channel, no current can flow. So, effectively IDS becomes 0 or very small, as we will see later on, and moment you try the inversion channel is created. Now it behaves like a device which where the current can flow from the source to the drain depending upon the applied potential. So, something like you move to the linear region, linear characteristics will be established, although it is not a linear but approximately you can say that it acts like a your resistor. Is a current controlled resistor, it becomes an effectively a resistive element where current is flowing from the source to the drain. But the entire function will depend upon how much voltage you apply between gate and the source. Now, to come back literally what happens in the event, we wanted to I do not know yeah. So, now if you look at the this is those of you who are familiar with the Fermi diagrams of the metal. We have a metal oxide and the PN semiconductor, PN junction, P type semiconductor, that is a substrate. If you look at it initially, we have the conduction, this is the conduction band, this is the valence band, and this is the EI, that is the intrinsic Fermi level. Now, since it is a P types material, normally the Fermi level of the P type semiconductor will be negative, and therefore you have this is the black line indicates the Fermi level of the P type semiconductor. Now, on the other side, and this side is above, you have the free space. Now, on the other side, this is this is a metal side, the Fermi level is, this is the work function difference in the metal. Now, initially if you look at it carefully, the EFP, when there is no bias is applied, there will be slight bending near the work side layer of the Fermi levels, but because the Fermi level, when you combine all the three materials, that is the metal, oxide and the semiconductor, the initial Fermi level must be the same across it. But so therefore, there will be some bending, but not enough. So, there will not be enough electrons in this region at all. Whereas, now if you apply a sufficiently large potential difference between this oxide and the semiconductor level, that means what is called the VGS, this is where gate is, the levels now start bending, the Fermi levels start bending, and if the applied potential is greater than the phi f, which is called the Fermi potential, that means you make it almost like a twice phi f. Now, you can see that the intrinsic level is bending below the intrinsic Fermi level of the EFP, which is the pure the P type semiconductor, and in this region now you can see therefore here it has become negative. That means, this is the property of a N type semiconductor, where the Fermi level is below the intrinsic Fermi level is below the EF here, and in this case, so this is the region now where you have now electrons available. So, as a consequence of this, as the voltage positive potential is applied between, this is your gate, the gate region, gate oxide, and this is the gate terminal. Now, when I am applying this is the substrate, as I am applying the potential between the gate substrate, assume that substrate is connected to the source, as I am increasing this voltage, slowly I am forcing the band diagrams, the Fermi levels to bend, and at a time will come when sufficiently large potential is applied, the Fermi level of the intrinsic Fermi level goes below the EFP, and in this region now we have electrons available. So, that is how the really from the band diagram point of view also you can explain or you can understand why we have the why the channel is formed. So, basically the channel is formed, if you look at it, as the consequence of the applied potential. So, any doubt, any question, particularly those of you who haven't gone through any semiconductor physics course. So, I have gone through little bit quickly, probably I have not gone into much detail, but I do not have much time also. So, if you can understand, therefore, now you can see that if I make it VGS equal to less than 0, now this bending of the diagram bending will take place in the reverse direction. So, now they will bend this way. If I apply VGS is negative, so that means essentially I am pulling more and more holes towards the surface, and therefore then there is no channel and the current will become 0, will not be available. So, both the band diagram as well as from intuitive understanding of the physics of this device, you can see that the characteristics will depend on VGS. So, that is one thing you must clearly understand. Now, next we will now look at how do I derive the expression for the current and the voltage, that is between, we have two things under our control. One is the VDS, that is the applied potential between the drain and the source, and the potential between gate and source. When the gate and source is above a threshold, current is flowing, but I can still control or go on increasing the VGS, and similarly I can go on increasing VDS, and what happens now? What is the current now? What is the expression for the current? So, typically, as I was tell you, now if you look at it carefully, the current voltage characteristics of an n-type NMOS semiconductor looks like this. So, here is the, as you go on increasing VDS above a threshold, then current goes on increasing, naturally it will, and so this is the region what we call the linear region, and it is the part I was explaining. I will come back to saturation later. And as also if you go on increasing VGS, the current will increase. So, the current now is a function of two parameters. One is the drain to source voltage and the gate to source voltage. With the effectively in digital circuits, we will assume current is 0 below A when VGS is less than threshold, current will flow, and then the voltage part we will analyze what happens to the output voltage in a NMOS type of circuits. Now, this is the saturation region. The why saturation will come back later, but the idea is, again I repeat, is that as I go on increasing below a certain threshold, the current is almost 0, is very small. Actually, it will not become exactly 0 because there will be some sub-threshold current. So, we will come back to that why those sub-threshold, but the bulk of the current flow will increase when the voltage becomes greater than the threshold. And we will see also what are the parameters on which voltage. So, now let us understand that what is the how do you analyze such a circuit behavior. If you look at the induced channel, if I go back to my previous, so this is where the induced channel is there. So, now there is a charge is induced. So, now what is the expression for this charge as I apply VGS, and so the expression for the charge is, therefore, if you can see again, now one more thing, the voltage here as it varies in the, if you say this is my x direction and this is the y direction, the voltage will vary along this direction. You have applied VDS here, the voltage is not constant at every point. And so, in this environment, what is the expression for the charge? Charge is VGS minus Vx, the voltage at a particular point, and minus V threshold. Why V threshold? Below that V threshold, there is no, effectively we do not have any mobile charge available, mobile conductor available, and COX is the capacitance per unit area. So, the charge current per unit, induced charge per unit area will be given by the capacitance times the voltage, effective voltage. Effective voltage is VGS is above threshold, VGS minus VTH, where you have now the really the inversion layer is formed, and the Vx as the voltage is varies, because the current is not, voltage is not constant at every point, and COX is the capacitance per unit area. Now, so the drain current, if you all know about from physics, drain current is nothing but the drift velocity, because as I have already said, current is flowing by drift, not by diffusion. The current, the electrons are pulled from the source to the drain and by the drift velocity. So, the drift velocity of the electrons, and then the negative sign is because we are talking about negative charge particles, that is the electrons. The charge, electron charge, this is electrons, so this is why negative is coming. So, Vnx equal to Qx times W, where W is the width of the channel. So, the current, drain current is Vnx into Qx times Vnx is the mobility or the drift velocity. Now, we will see that normally they will assume Vn to be constant, but that is not usually the case in this environment, but when in a very simplified initial analysis, we will assume that Vnx to be constant. So, now what is Vnx? Is the drift velocity. So, drift velocity will be dependent on the mu n and the electric field. So, electric field is mu nx into dV dx. Okay. So, the dependence of the Vnx on the mobility, the previous slide, if you look at here, we were talking about drift velocity. The velocity depends on the mobility and the electric field. Now, electric field is this, and this is the mu n, which is the mobility. Mobility also depends on actually will not be constant, but here we will assume that mobility is constant. And in this environment, therefore, IDS, the expression if you substitute it, it becomes like this. So, the current is now function of the voltage, and this is a simplified expression, by the way. It is a very simplified expression. It's we have made lots of assumptions. We have assumed that the mobility to be constant. We have assumed that after all, electric field here is not a purely horizontal electric field. You have the vertical component also, the gate to source voltage and the drain to source voltage. These are the two in the different directions. So, it is not a pure constant in that. So, we should have, but anyway, consider the other variation, but that makes the equation complicated. So, after substituting, and if you do the integrations now, the current equations will become something like that. Now, look here, the current now, this is where again I repeat VDS under the condition that VGS is greater than VT with threshold. Otherwise, the current is 0. So, under the assume the current is 0. As you increase the threshold, channel is established, and now this expression is somewhat quadratic in nature, because VDS square and times VGS minus VTH. If you assume that VGS and VTH is constant, which is the case, and then VDS square, this term, if I neglect it, VDS square by 2, then this becomes an ohmic equation. Is that all right? So, if you have any question at this point, you can ask. This is this eta is nothing but this entire product, mu n COX W by L. W by L is the width by length ratio. All right. So, this term is called the gain factor. The first term is called the process transconductance factor, that is mu n, the mobility, that is the permittivity of the dielectric, and T oxide is the thickness of the dielectric. This is basically a process parameter. Why process parameter? Because it will depend on how much thickness you have applied to the gate, that is gate oxide thickness, what type of oxide, that is what is the the permittivity of the oxide thing, and the mobility part of the electron. So, these are depends on the process conductance parameter, and this factor W by L, which will come repeatedly, is called the gain factor. And if you look at the equations now, it becomes somewhat, if you ignore the VDS square by 2, then IDS depends linearly on VDS. and this is the linear resistance. So, if I go back to my earlier diagram, it is this resistance. If I linearized it, this is the current voltage equation. So, this is the linear resistance of a NMOS transistor. So, now, so this is the equation for a typical equations which will be used frequently later on also. So, the current in the linear region will be of this type. Again I repeat, it is not a linear equation, that is a quadratic term involved, and that is how the quadratic, the curve shape is somewhat is not absolutely in a straight line. And second, it depends, this assume, there is an assumption that VGS is greater than V threshold, otherwise the current will assume to be 0, and then if we ignore the VDS by 2 part, then we have the pure linear equation. So, this the transconductance of an NMOS transistor is, if you look at it carefully, is called the GM, which is VIDS, but it is a linear region. It is like this. Now, we will come back to the saturation part. So, again now let us look at what happens slowly. Now, as I go on increasing the voltage between the drain and source, assume that gate, you have given sufficient voltage to the gate, so that there is a channel is formed. So, initially you will find that there is a channel is this entire region, this entire region has a channel. Now, as I go on increasing the voltage, actually the channel will be something, because voltage is here dropping to 0 at this point, V becomes 0 at this point, Vx is you take the difference. So, it is here, it is VDD, it is 0 here. So, the difference here is like this. So, you have a channel like this. Now, what happens if I go on increasing the voltage, that is the VD by, that is VDS, if I go on increasing the VDS. Now, as the VDS is becomes greater, then slowly what happens? What is the voltage here? If you look at the equation which we had derived while deriving the equation, the charge, we were looking at the VGS minus Vx. At the near the gate, as the voltage is slowly being increased, now as you go on increasing the voltage near the VDS, at this point the effective voltage that is available for creating the inversion layer also gets reduced, which is actually the VGD. This becomes less as I go on increasing the VDS. It is a VGS, it is VDDS minus VGS, and as you go on increasing the, when VDS becomes greater than VGS minus VTH, at this point you do not have VTH available to you for creating, that is across the capacitance, across the gate capacitance, there is not enough volt potential to create the inversion layer. So, at this point, so therefore, channel, there will not exist a channel. The channel, as I go on increasing, the difference between the VDS minus or VGS minus VDD or VGD, if you look at the what is VGD, is equal to VGS minus VDS. As long as this is the one which is going to be, which is actually create the channel in this region. Now, this one, as long as VDS is less than VGS minus VTH, I have no problem, because there is enough potential to create the inversion. But as I go on increasing the VDS in this region, now in this region now there is not enough potential to create the inversion layer. So, the inversion layer now since does not exist, slowly the channel, what we call the pinched off channel, becomes smaller and smaller. Channel moves towards the source region rather than closer to the source where the full potential is available. Then you have the entire effect of the VGS is available. But as I go on approach the drain, the effectiveness of the gate source potential for creating the channel gets reduced, and the channel becomes now pinched. So, what happens now? If you look at the current now, what happens? There is no more any free electrons available. Now, how therefore the current will flow? The current will flow because now when you have a sufficiently high voltage, the electrons which are generate or moving with a drift from the source to the drain through the channel existing, they have a sufficiently high mobility or velocity, and they will now with this velocity will go to the drain. No more new current, new generations of the carrier is available. So, effectively what will happen now, the current will now become saturated or it will not increase. See, this is what you must understand. So, why the channel pinch off? Because as I am going on increasing the V to VDS near the drain region, there is not enough potential available to create your inversion layer. And since the inversion layer does not exist, so there is no mobile carrier available, new mobile majority the carrier n-type electrons will be available by the applied potential. So, the current that is generated as a consequence of from the source to the drain will be moved with the drift velocity, and then this current will remain constant. So, this is the meaning of this. So, what we call the channel is now saturated. There is no more. So, the channel saturation will take place when VDS minus VG or VGS minus VDD is equal to VTH. If we always know, so at the point when VGD is equal to VTH, we know there is a channel formed. But moment VGD becomes less than the VTH, and there is no more channel in that region, and slowly the channel is becoming shrinking, and so the effective channel now, if you can see, has reduced to this. So, this is the L effective. So, it is in this region now the electrons being emitted from the source moves towards the drain. In this region it gets enough velocity, acquires enough velocity, and then it moves to the drain and reaches the drain. So, this is the mechanism of saturation, and no more current therefore follows. So, therefore, when you assume that the voltage difference between over the induced channel, so fixed at VGS minus VTT. So, if you look back to the previous equation, what you do merely in this, you put that VDS value equal to VGS minus VTH, this VDS, and then also VDS equal to this. So, the current is not supposed to increase. So, this equation is derived from the previous one by substituting VDS is equal to VGS minus VTH. So, this is why so, because at this point at this potential difference between the drain and the source, channel pinched off starts, and when the channel pinched off starts, no more increase in the current is expected, and so the current now with that increase in current with VGS will be the DS will be there. So, now you can see that is VDS becomes equal to it is independent of the DS. So, effectively it acts like a constant current source. The constant current, because the current is generated in the channel, whatever the shrink channel that is available, and it reaches the drain straight away. And if you look back to your diagram, it is this region. Now, you can say that still it is increasing Y show. So, that part we will see, but effectively if it had been a pure saturation, it should become flat, because in this region there is no increase as we have discussed. So, this is the reason why the current drain to source current is VGS minus VTH square is given, and this is called the saturation current region. All right. So, any question on this? So, this is the derivation of a NMOS behavior, and transconductance in this region here. Now, the question is, we will, so therefore, if you summarize all this, the current voltage relations of an NMOS transistor is IDS equal to 0 for this is again I repeat is a very simplified expression or first order approximation, you can say. It is less than 0 as long as VDS, sorry, this should be VGS, and there is an error here. I am sorry. So, as long as VGS is less than V threshold, the current is 0, and in the case of a saturation, this is the current is constant, it does not depend on VDS, and in this is the linear region characteristics. That is, VGS is greater than threshold, but the DS is not sufficiently large to have a channel pitched off. And so these are the equations we normally use for initially analyzing the behavior of the NMOS. So any doubt or any point, so this we will go on repeating these equations in our subsequent discussions. So any doubt you have, we can explain. Nothing. Good. So either you are familiar with it or anyway. Now, let us come back to the question that I had already mentioned, that apparently although the channels in the saturation region current should have flattened off, that means it should be truly saturated, it was not, it was increasing to some extent. That is, the characteristics were here. So, it is not, that is some increase in this region. The reason for this lies in these observations. We have already seen, as you increase the channel, the drain to source, there is a reduction in the channel length. So, L effective goes on slowly shrinking. Now, if you so therefore, if this factor, if you look back to the equations again, or rather this one, if you look at this L in this gain factor, L is no longer a constant. So, here we were assuming that L was constant, which is not true. As you go on increasing, L will effectively go on decreasing due to the rise of the increase in the drain to source voltage, and this is what is meant by. So, therefore, IDS is proportional to the 1 by L, and the reduction in the channel length will increase the IDS. So, the current will not be constant truly, and this is why the somewhat more better accurate expression will be something like this 1 plus. So, therefore, this you see, this is primarily what term is called the channel length modulation. The channel length decreases as VDS goes on increasing, and it is no longer constant, and so the reduction in the channel length has a proportionate effect on the current, and the current increases. So this is the much better approximation. Second thing which will, so the now before I go back to this, in case of a PMOS transistor where the carriers will be the holes, that is a majority, that means you have a source as a p-type material, drain as a p-type material, substrate as an n-type material. The channel, main majority carrier in the channel will be the holes. The basic, because the holes have a positive charge as compared to the electrons which are negatively charged, the equations are similar excepting now the sign changes. So therefore cutoff will be VGS should be greater than VTH to have a cutoff. So otherwise the VDS will IDS will be 0. Linear region is as long as VGS is less than threshold, but DS is greater than VGS minus VTH, we have the same linear equations. And in the saturation region, we have the VGS must be less than V threshold. So because now you have a positively charged carriers which you must allow. So therefore VGS must be negative to have that electrons to repel from the surface. That entire material you have to repel the electrons from the surface and have holes on near the surface to create a channel. So therefore VGS must be negative, and as long as VGS is greater than VTH, or rather not merely negative, it should be less than the VTH, and if it is less than VTH, the current will flow, and this is the equation. Otherwise the equation structure is similar, analysis is almost same. One thing we will go on repeating every time, there is a gain factor, it depends on the mobility. Now this mobility of the holes are almost 2.5 times slower than compared to the electrons. So electrons being a lighter element, they will move faster as compared to the holes. So the positively holes have these which are slower device, and that will have an effect on the sizing of the transistors, because if you want to have a same resistance, then as compared to the electrons, you have to have you have to size the p-type transistor accordingly to take into account the 2.5 factor. And so the I don't have the I'll have it later on. I think, let me see. So the PMOS characteristics are somewhat like this. That is a reverse. Actually, it's a reflection. It is a mirror image of it. So it will be somewhat in this region. I don't have the diagram with me here. So I'm sorry. I should have. I didn't. So now this is the holes. Now that another factor you should take into account in case of analysis of the transistor, particularly when we are going for a very low, very short channel devices, which is the case today. Why is the case today? Because we are decreasing the length of the channels very much. We have already reduced it to below 0.1 micron. Now as you go on decreasing the length, now if you look at the channel, this distance, that is the electric field, now goes on increasing, because you have the same potential VDS. Now as the length decreases, the electric field in this channel will be will be larger. Now as you go on increasing the electric field, you cannot expect the mobility of the electron to be constant. It cannot go on remain always constant with the increasing electric field. So therefore for short channel devices, we have to take into account the effect of, that is the high electric field. You will have to the velocity, that means what we are assuming, the velocity of the electrons were increasing, the increasing linearly with the electric field. If you remember the equations, it was increasing linearly. This is the case here. That means mobility was constant, and the the electrons were getting a velocity proportional to the electric field. I think you have seen this derivations of this equation here. The electron velocity was proportional to the electric field. Now, we cannot have a physical device, in fact, but the electron velocity will remain always go on increasing as you are making the electric field very, very high. So what really happens, electric field will, as the electric field increases, at a point of time will come, the electron velocity will be constant, it will not increase. So what you call the velocity, this is called the velocity saturation, and this in turn also has the effect on the entire analysis that we have done. So this is where that the VSAT, if they call the saturation, where the velocity saturation is reached, the model of the equation will become somewhat like this, and let's go back to this equation. So you will be having this kind of equations now. So the IDS, in case with the velocity saturation, will be somewhat like this. So this is what VSAT is, the saturated velocity. So we cannot expect go on increasing the linearly with the electric field. And today, when we are looking at the submicron level technology, velocity saturation will take place, and the analysis have to be done taking into account the velocity saturation effect. So these are you can consider to be somewhat second order analysis to be taken into account. When the class ends? Huh? Oh God! So I don't have much time left. Anyway, so I have analyzed the. Anyway, so I don't know. There are many factors on which the MOS transistor threshold voltage depends. I think I'll skip that part. Typically, the MOS transistor threshold voltage depends on many. You can look at I think you have been recommended some textbooks, I believe. There is a book by Rabbe. I'll give you the reference at the end. So that part you can look at. I think you should look at the book, because these derivations cannot be done now in this 15 minutes. I'll have to quickly wind up. So now you can see the expression for VGS. The threshold depends on the factors like what we call the depletion region charge density. This is as you are applying the VGS, you are slowly depleting the holes from there, and you are exposing the acceptor ions. Now that charge must be sustained by the external voltage, and this is the corresponding voltage part. 2 pi f is the voltage required for inversion, creation of the inversion layer, where phi f is the Fermi potential, and this term comes due to the defects, basically the impurities in this. And the expression, this VSB is normally 0, but you can control the threshold voltage by applying suitable source to substrate to the source voltage. So if the source and substrate are not tied together, then we can control the threshold voltage. This is one of the mechanisms we'll see in later designs where is used in some circuits. So the typical expression for this is the expression for VTH. This part is the substrate base voltage, and gamma is called the body effect or substrate bias coefficient. This is a typical equation that are used for threshold voltage. So the threshold voltage again is not a constant. It can be controlled by application of the bias between the source and the base, a substrate and the base. Now, the threshold voltage variation, this is again some of the things you must depend. Threshold voltage therefore depends on the length of the channel, width of the channel, and the VDS. Due to depletion regions of the source and the reverse bias drain junction, because if you remember that each source and the drain also forms a p-n junction. So, that there some depletion is there taking place. The third one decreases if you go on increasing VDS very large, because as you are increasing VDS, what you are doing simultaneously near the drain and the source region, you are increasing their depletion region. So, the effective length of the channel slowly goes on decreasing, and this is called the drain induced barrier lowering. This is the factor one must know. For very high drain to voltage, drain depletion region may get shortened. That means this is the depletion region. If you look at it, this is the depletion region near the drain, there is a depletion region near the source. Now, as I go on increasing these two regions, if they touch, then you have a punch through. So, that means when you apply a very high DS, and this is what is called the punch through effect. The narrow channel effects also increase at depletion. That means we are looking at the length of the channel. What about the width? The width of the channel also gets reduced in the current technology, and each channel will be separated by thick layer of metal oxides. So, these also creates near that below that threshold near that is oxides, you will have some depletion regions, and they will have the effects on the threshold. So, threshold depends on many factors, and you will see later on, due to the sum of the currents have to be controlled by controlling the threshold voltage. That means subthreshold currents. So, this is the term what is called that we have said that the below threshold current is 0, which is not the case in reality. Current will not be 0 in general. And what are the reasons where current depends? It depends on many things, particularly it depends on the gate to source voltage, and also that is the Q by KT. I think this expression you have seen during your p-n junction analysis. It depends on the temperature, it depends on the gate source voltage and VDS voltage, and so these currents have many components, and these are called the subthreshold currents in general. And the typical currents are like this: a reverse bias diode voltage leakage. So, here is a drain and is the source, the substrate. There is a reverse bias, and the leakage current will take place, and this leakage current will depend on the temperature of the device. So, this is a subthreshold. It has nothing to do with your this gate being creating inversion layer. And as some of you will probably look at the low power designs, so all these currents will also heat up the transistor, all the area. So, one of the objective will be to design transistors so that this reverse bias diode leakage currents are also reduced. And there are many technologies available today, and I think I will skip this part. I don't know how much I have time. It's only 5 minutes. I think I will skip these parts. Only thing I will just mention that the gate, that is the gate region, creates a capacitance, that is CMOS we have seen, and this capacitance normally we were assuming to be a flat. See, in this example we were thinking this is a straight line, but that does not really happen in physical world. The reason being that when you diffuse the n-type material, say here, this diffusion will not be terminated like this straight away. Some of the donor ions will permeate will move towards below the channel region also. So, effective channel length on both the drain side and the source side will be somewhat reduced compared to this, and this will have an effect on the drain to source capacitance, drain to substrate capacitance, substrate to source to substrate capacitance, gate to substrate capacitance. All these factors will come into analysis, and typical model will be something like this. So, you have the drain, source and gate. So, we have the gate to drain capacitance, drain to source base capacitance, similarly source to base capacitance and the gate. Now, all these capacitances will have effect on your transient behavior. That means, when you look at the AC analysis of the circuit, all these things will be switching characteristics of the transistors will have to take into account. And typically, I think I will skip this part. Typically, I will quickly go look at the some of the CMOS inverter. I think you have already been introduced what is a CMOS inverter. What really happens in CMOS inverter is that you have this is a p-type semiconductor MOS, this is an n-type MOS, and you have this is a load capacitance. And when V in and V out, this is a typical CMOS inverter. What are the advantages? Because the static current flow will be 0. And why so? This is a typical layout of a CMOS circuit, CMOS inverter. And you can see here, this is the PMOS transistor region, this is the NMOS, and this is the interconnect by polysilicon. This is the two gates are tied together. So, this is the two gates are tied together by polysilicon wire, and this is the PMOS and NMOS. This is the metal. This is the metal one which is connecting to your out, and this is the NMOS, and up one is shown normally by yellow for a PMOS and green by the NMOS region. Fabrication, I think I will skip. The only thing you can see, this is one is NMOS, another is PMOS. So, what we do, we lay them side by side. So, the two drains are connected together, two gates are connected together, and this is one goes to this is the DD, this goes to the PMOS side, and this is the NMOS side. And this is another way to two transistors. This is one is NMOS N well, another is a P well. Here you have the NMOS transistor, here you have the PMOS transistor, and you are connecting them back to back. This is the typical fabrication of a CMOS. The fabrication steps will be explained to you later. And the characteristics, what you do analyzing is that you plot these two graphs. Now, these two are interconnected transistors, you plot their graphs on the same scale, and now you can analyze the behavior of this through this path. So, this will be the typical path of a execution. I will come back to that. So, now let us look at how the transfer characteristics here. Has it been done, this one? Huh? Have they discussed it? So, here you can see that one transistor is in cutoff, the other is in the linear region. Similarly, here the other transistor is in linear region, and the PMOS is cut off, and in between transition takes place from linear to the saturation, both in saturation, and then one saturation, another linear, it goes like that. And the reason is that, again, based on these equations. So, these are the typical characteristics, and why so? We have already seen that as long as the voltage, input voltage is less than the V threshold of the negative of the n-type is cut off, p-type is now in linear region. Similarly, the other way. Only thing now, so the typical voltage current characteristics of it NMOS or CMOS is like this. I think this has been done, and the analysis is done by substituting the equations that we have derived. So, I will keep this part totally. Now, the model I was talking about, the condensed the capacitances. Now, when you try to analyze the switching characteristics of this transistor, you can see that all these capacitances have to be taken into account. This is the gate to drain of the n-type, gate to drain of the p-type, or this is the actual lump parameter model. Has it been discussed? Or probably it will be discussed when you look at the switching characteristics. So, typically this is an NMOS inverter model which will be covering. I think I'll skip this the derivations. I'll quickly go to the two things in the power dissipations. There are two components in the CMOS, is the dynamic power, short circuit power, and the leakage power. And the dynamic power is the power that is required for discharging and discharging of the output load capacitances, and it will depend on the voltage and the frequency. Now, higher the voltage, more will be the power dissipation, and so therefore, one of the current technology is that you want to reduce the power dissipation, reduce the voltage. Today's technology is that reduce voltage from 5 volt to 1.5 volt now, where we are even trying to get this lower. The problem will come essentially due to the noise margins. As we go on increasing the reducing the voltage, margins also gets reduced. So, that's one problem. Frequency, as we know, the clock speed is increasing. Every generations we have a higher and higher clock speeds. We are already in the gigahertz, several gigahertz region clocks. So, the frequency increases, voltage must decrease, and this is where the low power consumption circuits will be very, very important in the present design cycles. I think again I'll skip this. One, I believe this thing has been discussed. This is high and low voltages are VDD and VR. That means whatever the input and output, there is no deterioration in the output voltage. This will be 0 and 1. VDD will be 1 and V0 will be 0. There is always a finite resistance between the VDD or ground in the steady state. So, therefore, can be designed for low input impedance and making effectively less sensitive to noise. And major factor is that there is no static current flow. The static current flow means that either in the 0 state or in the 1 state, one of the transistor being off, there is no direct current flow, but there will be the current flow which is called the leakage current. So, the leakage current flow will take place, and it is one of the present day technologies main thrust is that to reduce the leakage current flow, and that part I was just mentioned the expression which is I went too fast. And however, as we go on decreasing the sizes, this leakage current becomes predominant factor, and fabrication technology tries to address these issues. Professor Chakravarti told me to quickly go through the scaling. The expressions we have discussed, see general in terms of L, W and area and all this. Now, what we are doing, we are trying to scale, means today we have a say we had a 1 micron technology, then we went down to 0.45, then 0.18, then again below that. So, essentially we are scaling the dimensions of the transistors. Now, as I decrease the dimensions, what are the effects on the major characteristics of this kind of inverters? And there are two types of scaling. One is called the constant voltage scaling. That means you keep the voltage constant, VDS, VGS to be constant, particularly VDS, and then reduce the dimension. Now, as you go on doing that, you have a problem. Problem is electric field goes on increasing proportionately. And as the electric field goes on increasing, all the problems, some of the problems I mentioned will come into the picture. Whereas, if I do the full scaling, meaning I reduce the voltage also proportionately, I reduce the size, reduce the voltage, and now we call what is called the full scaling. So, one of the objectives is that so that when the channel length is reduced by L by K, width also reduces by W by K, and the thickness is also reduced by K. K is a scaling factor. And the supply voltage is also reduced by K, as you can see. Then the junction depths also gets reduced now. Then the threshold voltage, this is where the problem starts creeping in. We need to reduce the threshold voltage by K. Now, to reduce the threshold voltage is much, we have seen that many of them are dependent on the process parameters. So, what you will have to do, you have to change the doping concentrations, one of the ways of doing it. So, if you do that, so the doping densities have to be increased by K times. So, when you do the P type or N type, the doping densities have to be increased, and if you do this factor, then you can see that electric field remains constant, current now decreases by k times, power consumption reduces by k square time. This is what is more important today. Your power consumption must be reduced. If you are reducing very, very thin small devices, power consumption, if it increases, it will heat up, it will destroy the transistor. So, heat dissipation becomes major problem. So, one issue will be therefore that full scaling, you reduce the power dissipation, and then but the gate delay also gets, you need to delay, that is which is used for the switching characteristics, that is how much input output delay, it will also reduce. So, the technology today is accompanied by the reduction in the sizes of the transistor together with the electric field and all the other characteristics. And why? So, the equations that we have derived somehow gives you an idea of what happens. And I think I will skip this part because I do not have time. Huh? I believe you will do the analysis of these circuits in using a SPICE. So far the theoretical analysis I have said are too complicated, particularly as you go on with the higher and higher order model. So, most of today analysis will be done in a computer, and the one of the basic techniques or tools that is used is by the SPICE. This SPICE was developed at UC Berkeley, and today there are many versions of SPICE, and it gets more and more complicated. Than the model of a transistor I had discussed is the most simplified model. There are now much more complicated models of the, I mean, you are taking much more variabilities into account, and the SPICE models are available, and we have the tools available here also. The full SPICE tools are available, and all analysis today are done at this transistor level using SPICE. And since you are a second year students, I am not sure you have you know about the electrical, how to set up the electrical equations. That is, you want to analyze the electrical circuit, you basically set up the Kashyap's current law and Kashyap's voltage law, and using that you set up the equations of the circuit. Now, the circuit, as you have seen, will contain the so many capacitances we have indicated. You have to take into account the variability of the doping concentration, the channel length modulations and all those factors, voltage saturation, and using the models, then you set up the equations, and these equations will be highly nonlinear equations. So, they do iterative methods of solving those equations, and the typical, you do not have to bother. There are now today the model 49, I think much more later on models, where you merely specify some of the parameters like thickness of the device, of the gate oxide, channel length and source resistance, and then using a computer to analyze. And typical model file, you do not have to look at this. These are basically the way you specify the model parameters and analyze. The typical analysis of the SPICE input will be something like that. I am not sure it is. Can you see this? It's not. No, it's not possible. Some of you can analyze the behavior. I think it's not. It's a screen dump of the. Anyway, typically the references I have mentioned are. You can look at this book. There are now later versions have come. The Rabi and Chandrasekhar. This is a very good book. These are the Berkeley groups. This book is the one I was referring to. The second one, it is available. That is Kang's book. And there are many other books today, but these are some of the standard textbooks. I didn't give you the reference books. All of them are available in our library. So you can see this. I hope some of the things I mentioned will be elaborated in subsequent lectures. Thank you. And any question you have? Probably too fast, isn't it? Huh?